Okay, take it away, Sean.
Okay, let me do a share. Show the PowerPoint.
Whoa.
And my dog is going to contribute, apparently. All right. You guys probably see it not in the quite right mode. There we go. All right. Oh, no, that's not going to work, right? Swap displays. How's that? Does that look right? Everybody can see that now?
That looks great.
Okay,
Yeah.
excellent. Great. Okay. Well, assuming my husky doesn't keep interrupting, then we'll be all set. Okay, so this is totally thrown in somewhat last minute. I got most of the slides from Clive Neal, and I have a big shout out to him on the second slide here. He's a colleague of several of ours from University of Notre Dame, who's been heavily involved in planning for lunar operations for a very long time from a science side. And I have recently been getting involved in white paper writing for the Artemis mission. And so it caused me to sort of go back and think a little bit about what Artemis is and how it relates to the Apollo mission and so on. And I know there's people like Yoshio who have been involved since the very beginning in this. And so I totally welcome other people to break in with any information they have or thoughts they have, because this is meant to be a little bit of a discussion, a little bit of a history and where we think we're heading. So without further ado, this is just one of the many, NASA-made illustrations of an astronaut in an Artemis spacesuit deploying some kind of science payload in the lunar South Pole, which is where the Artemis program is designed to go. But before we get there, let's back up a little bit. That is not working. Why is that not working? Interesting. Okay, try this. Oh, that did work. All right. So again, thanks to Clive Neal for a lot of these slides, which I've kind of merged a whole bunch of things together. And one of the first things I thought we should do is just, why is it called Artemis? For those who don't know, Artemis is the twin sister of Apollo, twins born to Zeus and Leto. It's kind of interesting, actually, because Artemis is really the right name for a mission to the moon because she is the goddess of the moon. Apollo is the god of the sun. So, probably got misnamed at the beginning, but nonetheless, they're doing it now. This is the name that will be given to the upcoming missions, but actually has an older history for use of thinking about going back to the moon than that, which I will get to. Why is I seem to not be able to do it with the arrows for some reason. Anyway, okay, so let's go back to the sort of history of Apollo. So this is obviously the first crewed mission to the moon was Apollo. The former director of the Glenn Research Center in Cleveland, Abe Silverstein, in 1960 was the one who chose the name Apollo because he basically thought it was a cool image of Apollo riding his chariot across the sun, and it was a grand scale event. Not really thinking about the mythology aspect, how Apollo is more linked to the sun, and it's really Artemis more linked to the moon. However, we should kind of get into why Apollo happened, and importantly, perhaps why Apollo ended. In thinking forward to the next human efforts on the moon. So this is sort of just a brief history of that. So Apollo actually in some ways started because Russia acted first. So in the 4th of October on 57, Russia, or the Soviet Union at the time, launched Sputnik, which was the first ever satellite, beating anybody else to space, so to speak. Likewise, in 61, Yuri Gagarin was the first human to go to space. So they were sort of way out ahead from that perspective. And then also in 61 and 62, there was these series of events that were, political conflicts and military conflicts that occurred that were sort of setting up, the next phase, if you will, of what was happening between the superpowers on Earth at the time. And so that's sort of, you should think about perhaps what happened with space with this backdrop of the politics of conflict that was occurring around the world at the time. And that really basically kicked off what was known as the space race, where the idea was, we had to beat the Soviets, but we were playing catch up. And there was a point sort of, if you will, of national pride, and also of sort of turning the public attention away from the disaster that was the Bay of Pigs and towards something more exciting and something to be perhaps more proud of as U.S. citizens at the time. And, you know, there's a good book, if you ever want to read it, by John Logston about the Kennedy and the race to the moon. That's you know, worth giving a read and getting some of this history out of. Okay, so what actually in the end happened is that the U.S. went on a series of missions, Apollo missions, 11 through 17 here, that actually did reach the moon. And it's interesting to look at how many actual hours were ever spent on the moon. So this is the amount of time away from the landers. So, you know, they ranged from sort of 2.5 hours on the first one, right up through 22 hours on the last one. And then this is the number of kilograms of samples that were brought back. And so this is literally the sum total of all you know, human gathered, and there have been no robotic gathered samples from the moon, that all of the analysis that has been done on understanding the moon from a petrographic standpoint could be done. So it's actually not an incredible amount of material if you want to think about it that way. And more importantly, as we get to, it was actually all from one basic area of the moon, and so not necessarily representative. The other thing to note is, if you're looking through this list here, is, you know, we had 11, 12, notice 13, of course, never made it to the moon. Then 14, 15, 16, 17, and then the program ends. So basically, it amounts to effectively, you know, a little more than 3 years, or 3.5 years of total efforts. And we've never been back with a crewed mission since, which is pretty amazing. I remember hearing an interview a number of years ago, but Arthur C. Clarke is sort of a well-known science fiction author. And somebody asked him, you know, in all of the interviewer asked, in all of the various technological developments and so on that have happened in the last, you know, say 30 years, did anything really surprise you about what happened, expecting some answer like the internet or something to be the response? And instead he said, well, the thing that was most surprising is that we went to the moon and then we stopped, which I always thought was really telling. So you could argue that in Apollo, US won the space race, but there was no real long-term plan for a next phase, right? And consequently, because there was no real long-term plan for a next phase, then you know, we didn't do anything for a long time. The Vietnam War was getting expensive. Somewhat the public had lost interest because we'd been there and it was almost old news. And so the program was in part canceled. And it was actually in part also canceled by politics. You know, as the transition of power occurred in the White House, the days of going to the moon was also disappearing. And a couple of events spurred it on. One was the interest in the Skylab. And so the plans for Apollo 20 were actually turned into what became Skylab. And that actually decision was made after Apollo 12. And then after the events of Apollo 13, the plans for Apollo 18 and 19 were canceled. And that was the end of Project Apollo. And here's just a little, you know, somewhat recent cartoon that kind of gets a sense of that. You know, remember when the idea of sending humans to the moon seemed like stuff of science fiction? You know, it's starting to feel that way again, since it's been, you know, 48 years since Apollo 17. Okay, so more recently, there was some interest in how about we get back to the moon, but not initially by the NASA side of things, but by some private companies, in particular something called the Lunar Resources Company, which then formed a nonprofit, an NGO called the Artemis Society in '94. And the idea was to establish a permanent self-sustaining base on the moon by 2002. Obviously that didn't happen. And the way they expected they were going to cover the costs was exploiting the entertainment value of having a lunar colony. Obviously this never worked, but it was an interesting idea. And it's the first use of the name Artemis as a next adventure to the moon, so to speak. And of course that is now the name of the current program. The next major thing to talk about is this thing that LEAG, which is the Lunar Exploration Analysis Group, has put together that was built or finally published in 2016, called the Lunar Exploration Roadmap. And what was truly different about this is it was a collaboration of scientists and private companies thinking about a way to have sort of a sustainable effort on the moon where the idea is if we do it just like Apollo, it's going to be, a short-lived series of mission activities, and then it's just going to go away. But if we can have other reasons to stay, then maybe it could actually become sustainable. So some of the ideas was to stimulate the economy, to enable humans to sustainably visit these more distant destinations such as Mars, to enhance sort of our role in space leadership as a country, and to, in the end, establish a sustained lunar exploration program with the acknowledgement that basically requires international collaboration. It requires what's known as in situ resource utilization, or ISRU. In other words, you get materials you need for a lot of things that you need to build, including potentially rocket fuel from the moon itself, and that the commercial sector would be quite involved. So that was the idea. And that this Lunar Exploration Analysis Group has been the center of these efforts and building this roadmap. So what is in that roadmap, because in many ways this helped define where we've gotten to today, is three basic themes: a science theme, pursuing fundamental science activities on the moon; a feed forward theme, where you use the moon as a base to go somewhere else, such as the most obvious thing being use it to get to Mars, because it's so much less expensive from a gravity perspective to take off from the moon than it is from Earth. And then a sustainability theme, which is to extend sustained human presence on the moon and eventually enable settlement on the moon. So that was the big ideas. Here were some of the, and I'm not going to go through this in great detail. They had these specific themes that I just mentioned, goals for each of those themes, specific objectives within those goals, and then even specific investigations that they all outlined. So it's a pretty good document. It's a living document. You can download it here from this website at the top of the screen. One big thread through this whole thing is that sustainability is the key. So don't abandon assets like happened at the end of Apollo with the famous, turning off of the seismometers and things like that, but instead leverage the assets, come up with ways to have commercial on-ramps into the program, and also international cooperation being critical. Okay. Some of the elements that were in the roadmap, and not all of these are in the current discussion of the Artemis program, and so that's an interesting dialogue, and we can have a little discussion about it. One is that you start off with robotic precursor missions, where you particularly pursue in situ resource utilization. So one of the big ideas was this mission called the NASA Resource Prospector mission, which I think might be able to go in 2022, but there's some question, and there's some announcements from NASA coming later this week. So we'll see what they say. The big question here is, can you mine the regolith, the sand-sized particles on the surface of the moon, for particular needs, such as oxygen, water, and helium-3 in particular. And then how long can you store those products on the moon in order to then use those utilizations to build a base to set this up as a place to then launch to go to someplace like Mars. So that was one key idea. A second stage of that, once you figure out if you can do it at all, then would be to ground truth and validate, how much resources are they? What's the form are they in? The amount, their location, and ultimately characterize the local environment of any place that you're going to ultimately have a more permanent presence. And right now the focus is on the South Pole, so asking those questions about the South Pole region. And then once you've done that, then you would then move into sort of a phase one where you do the prospecting. From this, once you characterize the environment, you'd figure out whether you can access and extract the resources needed. You'd quantify the geotechnical properties. So this is where things like even active seismic comes in to understand. And you'd actually start to traverse in areas around where you're going to build the resources. And you'd try to identify resource-rich sites for future missions. The second thing, if you're actually going to do this, is you got to mine. You have to think about the acquisition, the handling, the resource extraction, refinement, transport, storage, all that kind of stuff. The usability of those resources, how you handle the regolith itself, And then what kind of life, operational life, do you give to these systems? How long, what's the longevity of them in a lunar environment, which a lot of this is not known. And then you have to think about how you're going to mitigate for dust, because that's been a big issue on these even on the Apollo missions. And then lastly, you move into a sort of a production mode. So based on that phase 2, you get a much larger scale and thus more appropriate scale processing capability in the right place where great quantities can be produced and used to make extensive demonstrations, be able to do things like support life support, mobility, fuel for robotic sample return, kind of automated full-scale production, in order to really build towards an extended human stay on the surface. So that's in this roadmap. What came after the roadmap, just in the last, quite recently now, is that the White House announced their Space Policy Directive 1, which is a return to the moon. Their instructions were just to work with the private sector and international partners to figure out a human return to the moon. That was December 11th, 2017. And then last year in May, the NASA administrator revealed what is the Artemis program, which I'll give you a little bit of details about. And there was a really nice town hall about this at AGU last year for those who saw it. The idea is NASA will land the first woman on the moon and the next man on the moon by 2024. And that's still being said that might be reachable, although unless they say otherwise this week. Using innovative technologies to explore more of the lunar surface than ever before. They will collaborate with commercial and international partners. So this is basically what was in the roadmap, and establish a sustainable exploration note by 2028. So it's kind of a many-year program to get to the point of being quote unquote sustained. And then use this building out on the moon to be able to launch astronauts from there to Mars. Now, of course, this is just the current idea, but that's what's in the Artemis program. This little diagram below is sort of a pictorial tour of these different stages. So Artemis 1 would be first human spacecraft to the moon in the 21st century, which has already actually been done by the Chinese. Artemis 2, first humans to orbit the moon. And then this is really where this program comes in, which is a series of stages to build what's going to be called the Gateway, which would be a orbiter, a satellite around the moon that would first have a solar electric propulsion systems, then have a pressurized module attached to it, and then a human landing system that would launch and go back, to Gateway, and then a crewed mission that would use Gateway and this pressurized module system to go to and from the lunar surface. The other big things are capabilities technologically. So we have early South Pole robotic missions and first grounding truth if there are, in fact, say, water at the poles, which we think there is. These commercial lunar payload services to deliver the science and technology, and then large-scale cargo landers, and then finally the crewed mission to the moon. So those are all the elements to it. And then these are the additional steps that came since those announcements. So just in April of this year, the announcement is that NASA will send astronauts to the surface by 2024. The first time outside of watching historical footage where most people witness humans walking in another planetary body, and basically building on these footsteps, and robotic and human explorers will put in place infrastructure for long-term sustainable presence on the moon. And then they put out this document, NASA's Plan for Sustained Lunar Exploration and Development, many of which is hooked to the LEAG document, but a little bit different. So the key thing is, as the United States leads the development of this sustained presence on the moon, together with these partners, it will serve as a constant reminder of the limitless potential of humanity. And so they're going for sort of the excitement standpoint of this, but also lots of partnership, including the commercial world. These are the already named providers that will make various pieces of this system. And I'll describe 3 of these in a minute that are part of the commercial payload that would be sent as a enabler to all of these activities that are part of the Artemis program. So that's these commercial payload services that I mentioned before. And so this is a big place where the industry gets involved, but then also for some of these pieces, like building the pieces of gateway and so on, also are many on-roads for industry. And then once all that is done, the next concept is if you then have, you've been able to do all this, you figured out you can use the resources, you've got people there, you've got gateway in place, then you should have the ability to be thinking about using the moon as a launching point. And so this is the whole second phase of the Artemis program, which would be testing the landing and ascent capabilities, exploring the range of exploration, additional demonstrations of in situ resources, use Gateway to be augmented to have an international habitat so people can actually live on the satellite, and then use this as sort of a mobility platform to help transport things to and from the surface, and build an Artemis base camp for the human habitation there, and then expand this capability to enable the Mars mission dress rehearsal at the moon, and then finally do the dress rehearsal that sets us up for a crewed mission to Mars using the moon as the starting place. Okay. So note that they will leverage this. They also said in their April announcement that they will leverage the years of hard work on the systems needed to return to the moon in order that our return is sustainable. Now, what do they mean by sustainable? Well, there is actually some wording in there that we can take a clue on. They say it's able to be maintained at a certain rate or level, and also able to be upheld or defended for the long term. The first place it really talks about it in the document's actually on page 9, where it says specifically, we will develop new technologies that advance our national industries and discover new resources that will help grow our economy. So they're basically arguing that part of the commercial on-road and part of the sustainability of a lunar operation is also a sustainability technologically and economically back for the United States. And how that plays out is a really interesting question. By the way, this is the Artemis patch that for the crewed astronauts, or for the astronauts for the crewed mission. Okay, so this sustainability obviously requires involvement of industry and economic growth in order to, if you will, get a return on taxpayer investment through the NASA budget. And so the concept here is it's not just a once and done, you spend all the money and you get nothing back, but that there is some flow back, if you will, at the beginning, at the design stage. 3 companies have already been selected to design pieces of this. I mentioned that. So the Blue Origin is going to make the lander vehicle, the 3-stage lander on the new Glenn rocket system and the Vulcan launch system. Dynetics is doing the human landing system, which is a single structure providing the ascent descent capabilities from Gateway. And then SpaceX is doing the Starship, which is a fully integrated lander, which will use the Super Heavy rocket. So those are, and again, more lovely NASA images. And then their plan, if you will, for how you're going to make this sustainable is, not surprisingly, in situ resource utilization, ISRU, where the idea is to have a production of fuel, water, and or oxygen. No, and or, because it's unclear exactly what's going to work from the local materials, enabling the sustainable surface operations and decreasing the amount of supply needed from Earth. So the idea is to make an Artemis base camp that can be sustainable, because it's planned that the life support consumables and the rocket fuel can be sourced from the moon. So that's the key element. And some ideas of a couple different ways you could build a base that's on the surface, or you could build a base that's underground using lava tubes or other underground features. So the Artemis Base Camp might also include, and this is quite cool from a science perspective, a hopper that could deliver science and technology payloads to other parts of the moon, right? Which could be then operated by the crew at the base camp and refueled using locally sourced propellants. So such a transportation system, as well as refueling, would actually provide this incredible opportunity for exploring much more of the moon than one place that gets selected for the base. Okay, now one of the key things here obviously is water. None of this works if the water isn't available. There is now a lot of evidence that there is water, especially in the south pole of the moon and the permanently shadowed crater regions, but is it usable? Well, this is an interesting recent paper by Cannon and Britt in Icarus. And this was their a modeled attempt at the suitability, if you will, or ice favorability matrix, they call it, for being usable by humans at the surface. So it has to be within reach, it has to be large enough volumes and so on, based on the current remote sense data that we have. And they targeted some places in the South Pole with a much greater chance in these permanently shadowed regions for this to work than the North Pole. And this kind of logic is part of the reason why, although this paper came out more recently, it's part of the reason why the South Pole is being selected as the target for the Artemis program, because it has the best chance of having enough water to make this whole thing work. And how much do you need? This is a really interesting set of graphs based on the International Space Station data of if you have 1, 2, 3, 4, or 5, or 6 astronauts here, right? And how many Earth days you want to stay in a location versus how much consumed oxygen versus how much consumed water. And you can see actually that the oxygen values are high, but not out of the world. The big number that is kind of amazing is if you're going to stay, 90 days on the moon, you need 16,000 kilograms of water with 6 astronauts. So it's a lot of water required, and so that's why it's such a key part. And that's just for the astronauts, right? If you actually then want to make particular fuel combinations with oxygen and hydrogen engines, then you actually need additional water in order to run the hoppers and the lander refueling. So you'd actually even need more water than that if that's the direction they go with the technology. Okay, now there are some problems with this whole idea, and that's you're actually talking about mining the moon. Now, okay, now you're not going to be destroying lots of vegetation. There's maybe less environmental concerns for a quote unquote dead planet, which is not really dead because it's active and geologically anyway, in certain ways. But you are actually talking about prospecting and mining on the moon. And what does the law say about that? And it's interesting because we're in a little bit of a challenge here, which is that the 1967 Outer Space Treaty, which included the moon and other celestial bodies, is not subject to any national appropriation or claim of sovereignty by means of use or occupation. In other words, you can't just unilaterally go and start mining the moon without international agreement to this. I'm not sure our current administration would follow anything like this, but nonetheless, that is actually the current existence. So the Artemis program has had to think about this. There is a moon agreement in 1979 that came out that said the moon and its natural resources are the common heritage of mankind, and that an international regime should be established to govern the exploitation of such resources when it becomes feasible. So there was some thought, even in the late 70s, that we should be talking about this before it starts happening. And as usual, we haven't probably talked about it enough such that technology is getting to the point that the law is going to have to catch up pretty soon, most likely. So in May 15th of 2020, there was this thing known as the Artemis Accords that was put out by NASA, which are principles for a safe, peaceful, and prosperous future, very much thinking about those legal issues, right? And uses these words. So international cooperation on Artemis is intended not only to bolster exploration, but to enhance peaceful relationships. That's very nice. That transparency is the key principle for civil space exploration. And that's always been sort of NASA's, publicly described policies and plans that they put out. That's supposed to be the transparency aspect. And that we really need to make sure in international programs the systems are interoperable, because that ensures critical, safe, and robust space exploration. So think our bases in Antarctica and the needs for, the ability to support each other. You could have the same sort of circumstance on the moon. And you would need to make sure that your systems are interoperable enough that, if there were, say, a US base and another country's base, that they could support each other. So providing emergency and assistance to those in need is a cornerstone of any responsible civil space program. Registration of objects is at the core of creating a safe and sustainable environment. So this is a legal definition where you're actually registering what you have out in space, whether it's a satellite or in this case, a base on the moon. And that the Artemis Accords and their partners will agree with following NASA example by releasing all scientific data publicly to ensure the entire world can benefit from the exploration and discovery. I think that's a really key component to these accords. And of course, they're trying to get, a lot of countries to sign on. Okay. So some key precepts here is that protecting sites and artifacts will be important in space as is on Earth, including the artifacts that were left there from the Apollo program. And note that the ability to extract and utilize resources on the Moon, Mars, and asteroids will be critical to support safe and sustainable exploration. So again, they're talking about you've got to use the in situ resources and to avoid any harmful interference is an important principle of the Space Treaty and is to be implemented by Artemis Accords, and that all the partner nations will agree to act in a manner consistent with the principles and also to try to mitigate space debris, which is obviously a big issue when it comes to satellites. Okay, so summary of this part. Apollo was conducted in a spirit of competition with a very specific goal in mind. It relied on taxpayer money, was not sustainable. Artemis is attempted to be sustainable, at least envisioned to be, with the idea of needing a return on taxpayer investment, public-private partnerships, and use of local resources. So I think I'm going to briefly stop here and then maybe take some questions. And I have a few more things to talk about. So I'll just do a quick stop share, I think, and see. Oh yeah, John Lasser said, yes, right. So the volumes, I'm looking at the chat now. The volumes of rocks I quoted are just the US returned volumes that the Soviets brought back 300 grams from 3 lunar missions, absolutely. What is Skylab? Wow, that's an entertaining question. I remember Skylab falling when I was younger. Yeah, so it was, if you want to say, in some ways, the precursor of the International Space Station, and an attempt at building a location in space that would be sustainable. Yeah, John also says, "What is Skylab? Makes me feel old." I'm feeling the same way. Okay, so those are. I see no other questions. Anybody want to unmute and ask a quick question? We can do that before I move on to a couple more things I wanted to touch base on. Okay. Seems like nobody is doing that. Okay, I'm going to go back into sharing my screen mode then and talk just about a couple of other things. Share and go. Okay, so this is sort of the Artemis program as envisioned. What I wanted to now talk about is what's the science opportunities, and even the science opportunities for those of us who spend most of our time on, on the ice or in the oceans or airborne or whatever here on Earth. What are the ways that we might actually be able to play in this new expanding, especially geological investigations of the moon? One of them is that there's a mission plan that Yoshio Nakamura is actually a part of that is out there now called the Lunar Geophysical Network Mission that is being evaluated, which is the idea is to go after the moon as a geologic target and an end member body for understanding terrestrial planet evolution. And to try to understand the crustal composition of the moon and getting a sense of the way that terrestrial planets evolve by using the fact that the moon is its smaller size and thus lower heats means differentiation of the crust actually, or of the planetary structure essentially stopped well before it would occur on a much larger body, providing a much different set of compositions than we have to explore on Earth. And that, the current data are Mare basalt compositions are consistent with an origin from a source that derived from the cumulates in the mantle that crystallized from an early magma ocean and then potentially underwent an overturn event. But this is a very different sort of evolution than happened on Earth and might give some opportunities to understand fundamental processes. All right, so if we look back what Apollo taught us about the moon, it's very interesting because of the locations of where the samples, where the deployments actually were. So this is just a map of where Apollo networks were set up. So there was heat flow on 15 and 17 set up, magnetometers on 12, 15, and 16, passive seismometers on 12, 14, 15, and 16. these laser retroflectors that actually sense to the Earth and back on 11, 12, and 15, and on 2 Soviet ones. But they were all kind of located, in the area of the Apollo landing sites, which are on on the near side and on the edge of what is known as the Procellarum creep terrain, which is a very specific part of the lunar surface and not necessarily representative of the whole surface. So the heat flow was only at these 2 locations, and they were both near the boundary with this terrain, which is called this because it's a potassium, rare earth element, and phosphorus enhanced terrain relative to the rest of the world. So again, these heat flow are probably not representative, and we know we have lots of different crustal signatures, especially after the Grail data. The magnetometers were deployed at 3 different sites, but they weren't networked. And the Apollo 12 magnetometer and the Explorer 35 satellite jointly detected some low frequency electromagnetic soundings in the mantle, but again, only in this PKT terrain. And that the passive seismographic network, because of the narrow aperture, only can see part of the moon. So global crustal structure and deep structure is not fully resolved. And the retroreflectors that were used were only on the central near side and really need sites further away in order to add fidelity to what we know about, the tidal changes between the Earth and the moon, which is actually really important for things like, understanding the size of the inner core. So some of the main science questions about a new lunar geophysical network that have been put out there, and Yoshio has had a hand in many of these. How does the overall composition and structure of the moon inform us about differentiation of terrestrial planets? What's the state, structure, and composition of the mantle? Is it consistent with the magma ocean hypothesis, which I think most people think it will be, but there's a lot of variations of that. What's the present heat budget? And how could have the moon experienced any late stage magmatism, which is argued by some data? What is the crust mantle heterogeneity within the different terrains? And based on the size, state, and composition, how did the core form? And could the core have supported ever a global magnetic field? There's some evidence that at one point the moon had a little bit of a magnetic field from some papers, other papers don't agree. So there's some interesting debates about that. What is the bulk composition of the moon? How this can be related to the moon forming impact, which was when a Mars-sized body hit Earth and generated the moon in the first place. The ideas are that this lunar geophysical method will deploy identical landers containing seismometers, heat flow probes, MT, and the retroreflectors around the moon in order to examine all of these things. This will allow a whole lot more questions if done this way. And I just kind of a list of them here. Shallow moonquakes. Are they on thrust faults? Do they represent a threat to a future moon base? Do deep moonquakes occur on the far side of the moon? What's the true mechanism of deep moonquakes? Is the 500 to 600 mantle discontinuity that was sensed on the Apollo data real? And does it represent the base of the lunar magma ocean? Is there a partial melt layer at the base of the mantle? Do different terrains have unique heat flow budgets, and how does this reflect composition? And what's the sort of heterogeneity of the whole system as revealed by electrical conductivity? So those are some of the big ones. And just in the interest of time, I'm not going to go through this in great detail, but these are the main 4 objectives of this whole idea that you can see here: interior structure, composition, heterogeneities, and seismotectonics. And then these are some of the basic questions that still exist. These are various papers that have been written that have come up with the idea of the percent of the crystallized solid that makes up the moon. And you can see there's huge differences in opinion as to what this actually looks like. And so the only real way is to get out there with a real network to study these things. There are a bunch of secondary objectives, and I think in the interest of time, I'll skip these real quick, other than to mention the first one maybe, which is just trying to understand the current impact flux of the moon has some real implications, not just for thinking about near-Earth objects in general, or near-moon objects in this case, but also for thinking about hazards for any future base, and also to evaluate the seismic hazards for any human outposts. So I'll probably skip through that real quick. The basic design is they want 4 identical landers with the same exact instrument package globally deployed. They build them all at the same time, launch them together, but then deploy them one at a time. So if anything goes wrong, they can learn from their mistakes, so to speak. This is like the baseline idea. A threshold mission would be if this is too much, then to just build 2 identical landers deployed at a young Mari basalt site and then the antipodal site to the A33 site. So these are, this is a scaled back version of the same idea. Okay. And that's basically it from the standpoint of this mission idea that's out there that I know Yosho's been involved in for a while. That is not yet approved. It's out there as an idea for NASA to consider. What's happened just recently in the last month is that NASA has now put out a call for Artemis science white papers that are due today at 5 o'clock. So it's a little late if you haven't started writing, which are basically what can the astronauts, the crewed mission, do when it gets to the moon. If you have 2 people and they can potentially do as much as 2 EVAs, what should they do science-wise? And so they're asking for white papers for what the science should be that this mission could actually do. And I'm involved in a few of them. I know other people around the Jackson School and around UT broadly are involved in a few of them. So I thought I'd just give you a few of flavor of some of the things people are thinking about that the astronauts could do. One is they could investigate these low-bait fault scarps, or these low-bait scarps that are thought to be active faults on the moon. Use them both as the fact that they may be exposing some deeper material, but also to try to understand their origin and their age by investigating them directly. Another is to go after expanding the heat flux, right? We only have these 2 heat flow sites that are in the Apollo. So having one in the South Pole really adds to that. So that's an obvious one. Another obvious one is to have seismometers installed as part of, by the astronauts. And that there's an argument that you could probably get 10 times better resolution with the Artemis, with current technology. And if you had 10 times better resolution, you could actually get a whole lot more. This was the moon activity recorded, by the Apollo 14 station. And, if you translate that over to here, here's the meteorite. Here's the area that was actually capable of being recorded by Apollo. If you could do 10 times better than that in resolution, you could actually get to the point that you'd be able to record things like the reflected arrivals, the SCS, the PKP, and so on, and get some real additional capability of understanding the structure of the moon. So that's another pretty obvious one that people are suggesting. In addition, there's this general concept that you start the lunar geophysical network with a lunar geophysical package at this site. And, a baby version of this that could get rolled out by the astronauts. There won't be a lander for this, but they could roll it out and install, one of these geophysical packages. Also an idea that, of course, you might want to include a gravimeter on it. And then lastly, an idea that you might want to think about doing active seismic, because it actually was done on the moon in Apollo 17, and think about ways that you might actually want to do some refraction or reflection data to see the subsurface or measure some physical properties. And this is just a cartoon from Jim Head of the idea of what the shallow structure of the moon looks like and its approximate sound velocities. And this is actually measured sound velocities from Apollo 17 reanalyzed. And you can see how slow these velocities are to Earth velocities because of the lack of fluid-filled pore spaces, obviously. And that this should be done more than in one place. Now, of course, a big question for all of this is power. And so there's another white paper that's going in talking about power. One of the things that was done in Apollo 14 that is still really good technology to consider are these radioisotope thermoelectric generators, which are basically a nuclear source that uses the energy from the decay to actually drive it for a long time. But of course, you need things like batteries and so on. So one of the interesting ideas that just in some chats I thought you guys would find entertaining is this was an idea of how you might actually get greater offsets if you did a reflection profile on the moon and you can only walk so far away from the lander, putting your geophones out. And that's, you could put out a lovely little mortar assembly and send out explosives at different distances away from your geophones and get sort of a walk away experiment the other way by launching your, there's all kinds of interesting comments to make about grenades on landers and humans setting them off on the moon. But, nonetheless, people are thinking about creative ways and how you can do this with just 2 people. Okay. And I think actually I'm going to stop there. Well, other than to say, I'm going to hit the stop escape there for a moment, other than to say that there is one other thing worth mentioning to this group, which is that there's probably going to be an upcoming workshop focused on synergies between IODP, the scientific drilling program, and NASA on different types of science targets. And obviously the Artemis program and its geologic focus will nicely tie into some of the various ideas that people have been talking about doing with ocean drilling. So I think I'll stop there and take questions. And I can't see the chat until I hit stop, so I'll look and see if there's any more questions. Gail says, like the image of a female astronaut. Absolutely, they have completely committed to first woman on the moon. So at a minimum, there will be one female astronaut, and who knows, maybe there could be two. All right, any questions? This is really just meant to throw out some of the information that's out there and let people know about hopefully what's coming in the next few years.
Yeah, Sean, this is John Gerbach. I heard that Firefly up in Cedar Park is teaming with an Israeli group where they're redoing their lander to be able to do landings on the moon. Have you heard about that or at all?
I just saw their name listed on a set of slides that went by the other day, but I don't know any details about what they're doing. But I know I think they're in the running for some of the technology anyway. They weren't on that list noted that I had on one of my earlier slides, but I had seen them on some more recent discussions at some point. But I'm not fully in the know by any means on any of that. So,
okay,
yeah. Any other questions?
This is about past missions.
Yeah.
So I'm assuming that given the brief time on the moon, their seismic lines were pretty short. Is that true? Can you describe that a little bit?
Yeah, they were really short. God, I don't actually remember the full lengths. And I would argue the reflection side was less successful than the refraction side. You know, that some of the most useful information was the refraction data. Just simple physical. I mean, we you know, in some ways, simple physical properties is such a big deal. Because we only have it in the one place. So even the basic things, like if you're going to build something, you actually need the geotechnical information at that location. So, you know, while there's a lot of different ideas floating out there, in the end, you might have to do most of them before you ever get to the point of anything permanent. You know, and I would think that very much includes the need to do some active seismic. Now, how we do it, you know, maybe it's not geophones, maybe it's fiber optic cables. I mean, we don't, you know, there's a lot of ideas out there. You know, maybe the source is a, you know, a vibrational thing, you know, like we used in the rescrator, right? You know, that's been suggested that you could potentially do like a little mini vibrator that a human could operate. But again, you only have two people, right? You can think about any one of these little experiments we've done on Earth, we never do it with just two people, especially not in spacesuits. So, you know, this is not easy.
Cool.
Yeah.
Sean, I had a question.
Yeah, Brent.
Awesome talk. Yeah, I was wondering, like, is there discussion about like whether the technologies we currently have developed here on Earth, are those pretty much going to be able to just like immediately transferred and deployed on the moon, or is there a lot of changes that need to be done in order to adapt those to the different gravitational and setting? Like, for instance, I'm thinking all the equipment that's like on an IODP drill site, would a lot of changes need to be made in order to run those analyses on the moon? Yeah,
there's a lot of equipment that 1/6 gravity matters for, right? But there's also a lot of equipment that you have other reasons to think about shielding, right? You know, I mean, you have to worry about the dust problem, you have to worry about all kinds of things. So there's a whole lot of technological development that needs to go into operating in such a completely different environment. On the other hand, there's also a lot of experience that has already happened with all the various rovers and landers that have been used over the years in things like dust mitigation and things like, you know, what's the ways to do power. I just saw an email this morning. So one of the big issues is everything's trying to get smaller and smaller and smaller for the payload to be less and less in order to get done more at a time. So there's been a miniaturization driven by this too. But I just saw that the ESA, and I'll look up the number, but the ESA, their planned mission is that they're just starting the workshop on to figure out the details, is that they want to do 3 missions to the moon starting mid to late 2020. This is the European Space Agency, each with a 1.5 ton payload capacity. So that actually opens up some real possibilities for a number of other options, because at that point, you know, clever rovers and things could be used. Or one of the other big ideas, of course, is using robotics to expand what the human can do. Like you can envision, you can put a robot out there that can do a grid search for something like looking for, you know, water resources, you know, that while the human is off doing something else, right? So automated would make a lot of sense. Any other questions? Oh, yeah. Oh, yeah. Thanks, Mark. Mark just put out the announcement for the Artemis program link in the chat for those who haven't seen it. And I guess there is one caveat here, right? Which is that NASA is a mission agency, which means whoever's president affects things a lot. So this current, you know, return to the moon and then use the moon to go to Mars idea could actually change. You know, it could get scrapped, but it certainly makes a lot of sense from a dealing with the gravity well that is Earth. So.
Excellent. Well, thanks so much, Sean. That was a super fun talk. I think
Absolutely.
we all like talking about upcoming NASA missions and trips to the moon. Pretty exciting stuff.
Yeah, first one on the moon too. Woohoo.
Yeah, so thanks everyone for joining us for our first discussion hour talk. Next week we'll have Helen Stewart from Fugro joining us. So
oh, I see Ian. Yeah.
Hi.
You have a quick question?
No, it's just fascinating.
Oh, good. Okay.
I probably won't be around to see much of it, but you never know.
Never know. I would bet on you.
Thanks again. Very
absolutely.
Best to Jen.
All right, well, I'll see you all next week. Helen's talk is titled, "Please Do Not Take Cores in a Minefield, Creating User-Driven, Fit-for-Purpose Maps That Improve the Quality, Reliability, Safety, and Success of Your Research." So that also sounds super fun. So hopefully I'll see y'all then.
All right, thanks, Irma.